So in section 6.3, we get the chance to introduce a brand new function called the exponential function, which is really cool in my world. And so this is part one, and we're going to define that exponential function to be of the form c a to the x power. So for the first time, the variable is sitting up there as an exponent. So that's really important. A is called the base, just like we would have called it if we'd written 3 squared, 3 would have been the base. A is the base. It's important to note a couple things about that base. So A itself has to be positive. It cannot be a negative base. And the reason why it has to be positive is if we made it negative, such as -2, and then we stuck a fraction up there as an exponent, well, that would then imply the square root of a -2, which we can't do in the real number system. So that's why the base has to be positive. We can't use a negative in there. It also can't be 1, because if it were 1, then you would have 1 raised to a power, which is the same as 1 raised to any power, which is the same as even 1 raised to the 1/2 power, and it would just be a constant, so it would be a horizontal line. Not very exciting as a function. So those are the 2 restrictions on A. It's also called the growth factor. It's how fast your population, your function is growing. C out in front is your initial condition. For now, we're going to kind of ignore C. We'll pull C back into things when we go to do the application problems. But for now, we're just going to assume that C is 1. Again, it's a constant. Okay, again, for the first time, the variable is the exponent, which is why it's a different function. So our first example basically takes 2 XY tables of data, and wants us to determine whether the given function is linear, exponential, or neither. If it is linear, let's find a linear function. If it's exponential, let's find an exponential function. If it's neither, don't go any further with it. Okay, so I've copied the 2 tables onto the board. We're going to take a look at these. What we're going to notice is to get from here to here, what we're doing is multiplying by 4. Here to here, we're multiplying by 4. Here to here, we're multiplying by 4. And even from here to here, we're multiplying by 4. Well, when you're multiplying, that is not a linear function. A linear function, think about what that slope means. It has the same increase in y and the same increase in x. And that increase or decrease in x or y needs to be addition or subtraction. We're adding to or subtracting to. So let's take a look at this. If we take a look at this data set, we can see that sure enough, we are adding to get to the next term. And in terms of the x's, notice they're going up by 1. So because we're adding in terms of y, this is the linear function. And in fact, we can figure out the slope pretty straightforward. We're increasing in y by 2. We're increasing in x by 1, so our slope is 2. And they even gave me the y-intercept. The y-intercept is sitting over there at 4. So we can go straight into f of x equals mx plus b format. So that would be 2x plus 4. So as a linear function, that was pretty straightforward. Now back over here, because we are multiplying, this multiplying is what tells me this is an exponential function. And it's multiplying in terms of the y values. The x values are just going to be increasing by 1. But it's telling me that, and it's also telling me that the growth factor is a 4. So our growth factor is 4. So we're going to call this function f of x is equal to 4 to the x power. Now c over here is going to be a 1. Let's double check to make sure. So plug in a number. You plug in 1, 4 to the 1 is 4. That works. Plug in a 2, 4 squared is sure enough is 16. If we plug in the -1, 4 to the -1 is 1/4. So it works. So that's how we can tell the difference between a linear model and an exponential model. So the next thing we want to do is actually get a handle on what this graph looks like. So we're going to graph an exponential function. This time we're going to let the base be 2. So we're going to graph 2 to the x power. Don't leave that there, just a little more. So f of x, this is example 2, part A, is 2 to the x. It's the one we tend to start with. So what we're going to do, because we've never done this before, is build an xy table. So we use -2, -1, 0, 1, and 2. And then once we get it graphed, we're going to find the information and characteristics from that graph. Let's plug in the -2. So that would be 2 to the negative 2, a gentle reminder that the negative exponent moves that to the denominator and becomes a positive exponent. So that would then give me 1 over 4. To plug in negative 1, again, that's going to move it to the denominator. Now make it a positive 1. That just is 1/2. 2 to the 0 power, well, any number to the 0 power is 1. 2 to the first power is 2, and 2 squared is 4. So again, just a couple of reminders on what we're doing. So if I have x to the negative n, that's the same as 1 over x to the n. If I have x to the 0, I get a 1. So it's a background reminder of your exponentials. Okay, let's go graph these. So at negative 2, we're at 1/4. We're really close to the x-axis. At negative 1, we're at 1/2. At 0, we're up at 1. At 1, we're up at 2. And at 2, we're up at 4. So we get those 5 points. And when we connect them, it looks something like this. And there's our exponential graph. Wow. So do you think this graph is ever going to go below the x-axis? In other words, is there some value I can plug in for x where it's going to force this thing to go into either 0 or negatives? Well, the answer is no, it definitely is not. That implies there's an asymptote sitting there, and there sure is. There's an asymptote sitting on top of this axis. So we have a horizontal asymptote. And there's our graph. So let's find our information. So our domain is negative infinity to infinity. In other words, you can plug in any value you want for x. And again, that means any real number can be plugged in for x. So you can plug in rationals, irrationals, decimals, fractions, positives, negatives, anything you want, including 0. The range, however, is a little more descriptive. We just said it's not going to go below 0. So it's going to start at 0 and go off towards infinity. It is exclusive. It's never going to touch 0. So we use a parenthesis there. There is no x-intercept. So for the x-intercept, there isn't one. We're going to write a 9. For the y-intercept, that's 0, 1. We plotted it. It does have an asymptote, a horizontal asymptote at y=0. It is an increasing function. So it is increasing as you move from left to right. It is going uphill. And it is 1-to-1, which is important for us because it is 1-to-1. We know that it's going to have a graph or an inverse function, and we'll worry about that in the next section. So there's your basic exponential graph. In the next part of the videos, we'll investigate what happens when we change that base.